In today's assignment, we're going to work with similar triangles and indirect measurement. So we're going to solve proportions, and then we're going to determine if two triangles are similar. And then we're going to use properties of similar triangles to solve indirect measurement applications. So cross product is just a method used to solve proportions. Proportions, remember, are two equal fractions, and I like to call it the Hart method, and I'll show you why. If you're given, here's our two equal fractions. So if my Hart method says that you take the bottom times the top, so A times D will give you just AD, and B times C, and you leave the equals in the middle, and you get a Hart. So I always teach this. That's how I learned how to do this a long time ago, and it's really stuck with me. So I like to call it the Hart method, but some people call it the cross product. So anyways, that will give you AD equals BC, and then we can work from there. So on example 1, we're going to solve each proportion. I'm going to use the Hart method. I'm going to take 5 times 12 is 60 equals 18 times x. And then to solve for x, we have to isolate it. To isolate it, we divide by 18. So x, the 18's divide out, we're left with x equals 3 1/3, or 0.3 repeating. On our second one, on B, same idea. We take 4 times 7 is 28 equals 16 times y. We divide by 16, and y equals 1 3/4, or you could say 1.75. Similar triangles, these are when two triangles have the same shape but not necessarily the same size. Your angle-angle similarity is if two angles in one triangle are congruent, that means exactly the same, to two angles of another triangle, then the triangles are similar. So I have here some symbols. If we can show that A is congruent to D and B is congruent to F, then we can say that these two triangles are similar. And I wanted to point out that the way that we label these or order them is very important. We can see that angle A has to line up with D of the second triangle, angle B has to line up with F, and C has to line up with E. So our job is to try to prove that those two angles are congruent, and then we can say that the triangles are similar. So on example 2, it says determine if the two triangles are similar, and if so, write a similarity statement. So to determine this, you're going to have to find the missing angle in both of those so that we can prove that we have two pairs of angles that are congruent. We can see here that P and T are already exactly the same, but we need to find those other angles to verify if they are similar. So to do that, we're going to add 20 and 40, and then we're going to take that, which is 60, and subtract it from 180. So that gives us 120. You can probably already tell that R and V are not congruent, so most likely U and S are not, but to verify that, we'll go ahead and add the 20 plus 115, which is 135, and subtract that from 180. And that gives us this leftover angle of 45. And here we can show that only one pair of angles are congruent, so these are not similar. On B, we have A and E are congruent, and then one other kind of angle. If you guys remember, two lines that intersect like this form the X. I call it the angles that are the X, and these are congruent. Those are known as vertical angles, and all vertical angles are congruent. So here we have shown that two different pairs of angles are congruent, so these triangles are similar. So triangle A, B, C. The first triangle, it does not matter how you label it, but the second one, it does matter. So triangle ABC is similar to triangle. Because I started with A, I've got to start with E for my second one. and I went to B, we can see B is going to line up with D and then to C. And that's your similarity statement. Okay, direct measurement. These are lengths that are easy to measure, like your arm, your height, your wall, the diameter of a volleyball. These are easy to measure. We have indirect measurement. These are lengths that are difficult to measure directly, like the height of the Empire State Building, the distance to the moon, the distance across a lake, the single bacteria. It's so small it's really hard to measure. When these occur, we try to set up proportions to be able to find these lengths. Thales, he was the first Greek mathematician, and he was the first to determine the height of the pyramids by studying the shadows made by the sun. So he wanted to know this height there, call it x, and he did it by observing a shadow of a sun made here, and then used a tool here to make another shadow, and then he related those shadows. So is there enough to determine that there are similar triangles? So we can see that this big triangle and this little triangle, they both share an angle right here. And if you both notice that these are perpendicular, so is there enough to say that there are similar triangles? Yes. So what are the congruent angles? I would say the shared angle here, and also those that are perpendicular there would be the congruent angles. Okay, so this says we have a fire hydrant 2.5 feet high. I'm not going to draw a fire hydrant, but I'll draw something here. It says that it's 2.5 feet high. It casts a 5-foot shadow. So it's casting a 5-foot shadow. We also have a street light. It's a lot taller. That casts a 26-foot shadow at the same time. We want to know how tall that street lamp is, or street light. So we're going to actually use similar triangles because they have the same angle from the sun is creating a shadow. So I'm going to actually look at my first triangle and write my two values. It really doesn't matter, but this is one way you can solve this. And because I chose the 2.5, that was the height of the hydrant, then I need to use the height of my street lamp on the top of the fraction equals 26 or over 26, so that the shadows are both on the in the denominator of my fraction. From here, I would just use that Hart method that I talked about earlier. We get 5x over here, and we get 2.5 times 26, which is 65. And then to isolate x, we divide by 5, so x is 13. Some of you already recognize that these were half of each other, so you could say that because they're half, we could take half of 26 to get 13. And that would be 13 feet. Hopefully you can see that. Okay, example 4, it says in the figure triangle DBA is similar to triangle ECA. Randy wants to know the distance across the lake. So I'm going to take my smaller triangle here, and I'm going to find the lengths for it. I'm going to take that long side, 320, and compare it to the 40, like I would in the bigger triangle here. So in the bigger triangle, I don't know D. Now D corresponds with the 40, so I know that has to go on the bottom of my fraction. On the top, remember I need the whole length of that side, so I actually have to take 320 plus 162, which gives us 482. Okay, from here we're going to apply that Hart method where we take 320 times D is equal to 40 times 482. This is 19,280. And then to isolate D, to get D by itself, we divide by 320. So D equals about 60.25 or 60 1/4 of a meter. So hopefully that'll help you with your assignment 9-4, similar triangles and indirect measurement. Good luck.